Welcome, everyone. I'm pleased to have this opportunity to discuss PLC application technology with you. I'm Werd Skong, a lecturer and researcher at King Mongkut's University of Technology, North Bangkok. My expertise spans energy storage, power stability, and vehicle control systems. With experience in areas like battery modeling and AI, I look forward to sharing an overview on PLC applications in industry today. My slide consists of three main topics. I will begin with the current status of Thai industry. Thailand is transitioning towards Industry 4.0, but it is not yet fully developed like in more advanced countries. We are focusing on the implementation of IoT and AI in production process. As we can see from this slide, Thailand's industrial automation market continues to grow across all sectors each year. The automation pyramid highlights that PLCs play a crucial role by connecting and controlling machinery at the low levels, while linking to monitoring, management, and production planning systems at the top. This simulation is used to design the automation process for welding high-pressure tanks. In this setup, the system operates automatically, with human operators responsible only for monitoring. This design has been implemented on an actual production line. The picture on the left displays the PLC, while the right shows robotic arms controlled by the PLC. This photo was taken at a factory in Rayong province. The PLC system consists of 6 main components. First is the programming device, which sets up control programs. Input devices receive data from sensors, like temperature or pressure signals. The main power supply powers the entire PLC system. Output devices control actuators, valves, and motors. Next, the communications interface allows data exchange with other PLCs or display systems. Finally, the processor executes commands and controls actions based on programmed logic. These components work together to enable effective automation control. The working principle of a PLC is based on a cyclic scanning mechanism. Its core workflow is as follows. 1. Initialization. When the PLC is powered on or reset, it first performs a self-test, including hardware checks and software initialization. The PLC loads the user program and system programs into memory. It configures the input, output, I/O modules to ensure correct connection with external devices. 2. Input sampling. The PLC reads the status of all input modules, which may come from buttons, sensors, switches, etc. The PLC stores these input signals in the input image registers, which are special areas in memory used to store input signals. 3. User program execution. The PLC processes the data in the input image registers according to the logic of the user program. The user program usually includes logic instructions, such as AND, OR, NOT, timers, counters, comparison instructions, and other elements. The result of the program execution will affect the data in the output image registers. 4. Output refresh. The PLC writes the data from the output image registers to the output modules. The output modules use this data to control external devices such as motors, valves, indicator lights, etc. 5. Cyclic scanning. After completing the above stages, the PLC immediately starts a new scan cycle, and this process continues without interruption. The PLC scan cycle is very short, usually at the millisecond level, to ensure real-time performance of the system. 6. Interrupt handling. In certain cases, the PLC may execute interrupt programs. These programs interrupt the normal scanning process and are executed when specific events occur, such as input signal changes or timer expiration. 7. Communication handling. During the appropriate time in the scan cycle, the PLC handles communication tasks with other PLCs or host computers for data exchange. The working principle of a PLC has the following characteristics. 1. Cyclic nature. The PLC continuously repeats the above scan cycles. 2. Determinism. Due to the cyclic scanning mechanism, the operation of the PLC is predictable and deterministic. 3. Real-time performance. Although the PLC operates based on cyclic scanning, its scan cycle is very short, meeting the real-time requirements of most industrial applications. 4. Reliability. The PLC is designed to withstand industrial environmental interference, ensuring stable system operation. Through this working principle, the PLC can effectively control and manage complex industrial processes, improving production efficiency and safety. What about the communication network of the PLC? Let's start our exploration now. 1. Communication protocols. The PLC supports multiple communication protocols, such as Modbus, Profibus, and Ethernet, to facilitate data exchange with other devices or control systems. 2. Network structure. The PLC network is divided into the device layer, control layer, and information layer. PLCs at different levels are connected via respective networks to enable data integration and sharing. Next, let's learn about PLC safety and protection measures. 1. Safety functions. The PLC has safety functions, such as emergency stop, safety monitoring, and fault diagnostics to ensure the safety of personnel and equipment. 2. Protection rating. The PLC's casing design meets certain protection ratings, such as at 2.0 and at 5.4, to adapt to different industrial environments. This slide provides an example of how a PLC is used to manage and control load distribution in a solar power system. You can see that the PLC acts as a bridge between the equipment we want to control and the monitoring system, which connects human operators for oversight.